Welcome to this presentation ahead of CANS 2020. I'll be talking about our work on semi-commutative masking, which is a new framework for isogeny-based protocol. This is joint work with Emmanuela Orsini, Christophe, Petit, and Nigel Smart. So in this presentation, I'll be starting with giving some background on supersingular isogenies, explaining a bit the concept, giving some notation, and presenting the supersingular isogeny key exchange protocol, which is a bit analog to the Diffie-Hellman protocol. Then I'll be talking about our main contribution of semi-commutative masking structures. I'll give a definition, some computational problems, and explain how we can instantiate it, namely with supersingular isogenies. And finally, I'll be describing the oblivious transfer protocol that we propose with some of its security features and some of its applications. So to get right into it, in our setting, we take Q to be the square of a prime, P, and we are concerned with supersingular elliptic curves over the field FQ, so defined by coefficients over FQ. So these isogenies are maps between two curves, so there are group homomorphisms from the group of points on one curve to the group of points on the other, and in some sense they allow to move from one curve to another in the graph of supersingular elliptic curves. Now, the thing to know is that for every prime L that doesn't divide P, there are L plus 1 isogeny classes originating from any supersingular curve. So that means that in this graph of curves, whenever from any node, any class of curve, there's L plus 1 different ways, different edges to move to a different curve. And this is how the computations take place. We walk across the graph in some sense. Now, for every subgroup K on the group of points, we can in fact identify a unique isogeny class with that kernel. So this gives us an easy way to represent isogenies. We only have to specify their kernel, and then we can say that phi takes E to E mod K, and that's the step taking in the graph. And so we'll be particularly working with subgroups of the torsion EM, so where M is an integer, and this group is simply the group of points of E whose order divides M. So given this background, how do we do something that's key exchange-like? So the first thing to do is to take a bit of a special prime, where it's going to be a power of LA and a power of LB, both of small primes, times a cofactor and then plus or minus 1. So these small primes can be 2 or 3. For efficiency reasons, this means the protocol can run quite quickly. So the thing is that when we want to represent the SIKE protocol on paper, it looks a little bit like this, and that's quite a complex way to write it down. We have to generate the alphas, the betas, the subgroups Ks, the phis. So we think that that's a bit of a barrier to protocol design in the isogeny setting. It's a bit difficult to understand what's going on, what is hiding what, and how information can be manipulated. So ideally, we would like to have something that looks a bit more like this, where we have a shared curve R, and Alice, for example, can generate a mask A and apply it to this public curve to obtain a masked version. Bob can do the same, and they can exchange these masked values. And then each on their own, they can apply their mask to the other party's masked value. And with some form of commutativity, these two values are in agreement, and the key exchange can take place. So this is where we started off a little bit with this idea in mind of simplifying these protocols for our definition of semi-commutative masking. So a semi-commutative masking structure is first of all defined over a set X. So we're going to act on a set of elements. Now, each element in this set can be represented in a different way within our structures, and we label by Rx the set of all representatives of a given element. So to take as a running example the discrete logarithm setting, we can let the set be the cyclic group of points of order p within the field fq. And in this case, we can either, for example, let every element be its own representative by an integer or so, or we can take Rx to be, each element can be multiply represented by itself and itself shifted by p or even by 2p. So even though these would be different integers, they would represent the same group element. So this is why this idea of multiple representations come from. So then we have masks, and these masks are maps from one representative to any other. So in our discrete logarithm example, such a mask would be exponentiation by a for an appropriate value of a, and taking modulo the correct value. So in this way, the idea behind the name mask is that this would hide the value we started from, obviously. So, sorry, not the value we started from, but the mask itself. Then we can have masking sets, which are just sets of such maps. And we then have to define what we mean by invertible and semi-commutative. So masks can be invertible if for any element and any representative, we can define an inverse mask, such that applying first the mask and then its inverse gives a representative of the same element. So the two things to note here is first that we only obtain a representative of the same element, not necessarily the same representative, but we do require that elements can be efficiently computed from any of their representative. So for all intents and purposes, we come back to the same element. And the second thing to note here is that the definition of the inverse depends on the initial representative. So given a mask and an element x, two different representatives for x can yield two different inverse computations. So we just have to bear that in mind. So then we say that if all masks within the set are invertible, then the set itself is invertible. And in our running example, for any map G which takes G to the A, the inverse is G to the 1 over A, simply. Then for semi-commutativity, the idea is that masks that belong to two different masking sets should commute with each other. So again, we have the same caveat that they cannot give the same representative, but we specify that applying first one mask and then the other, or vice versa, should give two representatives of the same element. And if this applies for every mask, we say that the whole structure is semi-commutative. So the semi means because of the requirement that two masks have to be from different masking sets. So we cannot guarantee that two masks from the same set will commute with each other. So then defining this structure like this gives us a couple of computational problems which have some analogs into the more traditional discrete log setting. The first is the demask problem, where one is given a masking set index, a base representative R, and Rx, which is the product of a random mask applied to R. And the challenge is to return this mask. So in the discrete logarithm setting, this is simply the discrete logarithm problem. So given a random A and G to the A, one has to return A. So the second problem we have here is the parallel problem. Given the usual tuple G to the A, G to the B, here I'm using discrete logarithm notation to make this very familiar, then the challenge is to compute G to the B to the A. The second problem we have is a variant of the first, and here the challenge is to compute G to the B to the 1 over A. So depending exactly on how you formulate your CDH problem, this can be proven to be equivalent in the discrete logarithm setting. For example, in a supersingular isogeny setting, this is not so clear. But because there is still the computation that involves an unknown masks, we conjecture that the hardness is the same. Then we also have the parallel both problem. So here we have a bit of a new version where we're given two elements, g to the a1 and g to the a2, and the adversary can compute either to the power of a1 over a0, sorry, or a0 over a1. It can choose. So again, it's a bit of a non-standard, but because this also only uses exponentiation or inverse of exponentiations, we conjecture that this problem is similarly difficult. So then, how does one instantiate these masking structures? What actual constructions can we use them with? So the first is anything that's a group action. So here we have a group G that acts on a set X, and each element takes an element of the set to another. And defining the masking structure is quite straightforward. So the set is the same, and every element is represented by itself. And for the masking sets, we just use two copies of the group G, assuming that G is commutative. Because then any element of G commutes with any other element of G, and we satisfy the semi-commutativity requirement, and because G is a group, inverses are straightforward. So in the discrete logarithm setting, again, X can be the subgroup generated by G, and the group is just exponentiation maps. But this also captures the more recent setting of the seaside schemes, where here the group is actually the class group of the endomorphism ring of supersingular elliptic curves over Fp, and not Fp squared. That's the main difference. And so here what we have is for any order, we can let X be the set of elliptic curves that have this order as their endomorphism ring. And then the group G is the class group of this order. And then we get a group action, which can be captured by our semi-commutative masking definition. The other different instantiation that we propose is the one of supersingular isogenies over Fp squared. So here the taking Fp squared makes a difference because in the seaside setting there is a sub-exponential quantum algorithm that can help solve some of the difficult problems, and such an efficient, well, almost efficient algorithm is not known for the setting over Fp squared. So, but with this we have the heavier notation that we had from the beginning. So here we take X to be the largest class of supersingular J invariants over Fp squared. So the largest graph of curves where all the curves are isogenous to each other. And then we can say that for each J invariant, each node, there is a canonical curve Ex. So this can be defined by the coefficients of the curve. So we set this to be the first element of our representatives. And with each such curve, we actually let the representative be also a set of n bases of torsion points. N can be 2, 3, 4, or more. In the SIKE setting, for example, n was just 2. We had 2 torsion subgroups that we were working with. But the idea is that each of these torsion subgroups can be represented by many different bases. So we allow the representative of any J invariant X to have these many bases which all represent the same subgroup. So given these elements, we can then define our masking sets. So in the same notation as before, well, we take Z mod Li EI for I going from 1 to n, and we take the projective line defined over this group. So this projective line is the class of points AJ, BJ, which can be identified with the cyclic subgroups of the torsion subgroup. So any cyclic subgroup will have multiple generators, but when you express these generators in the bases Pi, Qi, each coefficients alpha and beta will all belong to the same class in the projective line. So this class maps one-to-one with the subgroup. So this is why we use the projective line here. For inverses, here, I didn't mention this at the beginning, we use what we call dual isogenies. So for every isogeny there exists a dual isogeny. So if the first was from E1 to E2, the dual isogeny maps points on E2 back to points on E1. And with it's not a perfect inverse in terms of points because it does apply a multiplicative factor, but in terms of curves, it's sufficient. So here we will use this as our definition for inverses. And finally, semi-commutativity holds because of the coprimality of isogeny degrees. So the isogenies, which are a degree of power Li and another which is a degree of power Lj, can be applied interchangeably, and we will arrive into the same isogeny class, so the same curve class, sorry, the same J invariant at the end. So we have here all the elements that we need for our semi-commutative structure. And the computational problems that result from the instantiation of the problems I defined earlier are small generalizations of the standard SIDH problems, so the same security problems that SIKE, SIDH, and these constructions rely on. And the generalization here is that instead of having only 2 powers of primes, we have up to n, but for our protocols we in fact have n equal to 2 or 3. And so the security assumption is very much the same. So talking about protocols, I'm now going to give you a quick recap of a quick presentation of our oblivious transfer protocol. So it's based on what is called the Shamir 3-pass protocol, but it's been compressed to fit into only 2 rounds of communication. So here I'd like to highlight the fact that our structure gives us quite a strong constraint, which only allows us an exponentiation only mechanism. So this is where the discrete log notation is kind of appropriate as long as we only use exponentiation operations. So we cannot multiply group elements together. So to go over the protocol, Alice and Bob have 3 elements in common. A generator G for the group, or a single element or a single representative, as well as 2 randomly chosen ones, G0 and G1. The receiver Bob here also have a choice bit, so the point of the oblivious transfer protocol is that Alice will obtain 2 random strings, here M0 and M1, and Bob will choose one of them, and Alice will not know which one Bob chose, and Bob will not know the one that he didn't choose. So Bob will start, generate a mask B, and mask the common element of his choice. This masking hides his choice, and so Alice will reply with the key exchange protocol, in some sense, with G to the AB. Now on the side, Alice also applies the same mask A to both the 0 element and the 1 element, and that gives her 2 random values that she can use. Now Bob instead will use the key exchange value, but will remove his mask 1 over B with the inverse property, and the commutativity of this will mean that it will cancel out his original mask. So then he obtains his choice element, but with Alice's random mask applied to it, which is therefore one of the random values that Alice has used. By then generating pseudo-random keys from these 2 values, Alice and Bob can use symmetric cryptography techniques to exchange arbitrary strings, and thus gives us 2-round string OT. So unfortunately for this particular protocol, we only have a security proof against passive adversary in the UC framework, which is already a good result, but we also have a second 3-round, this 2-round oblivious transfer protocol does allow us to do quite a few things. So the first thing is that it gives us a 3-round OT extension protocol. So OT extension is when, after doing a first OT, the 2 parties can then use the material that they generated to essentially compute a much larger number of OTs. So realizing this with only 3 rounds is quite efficient. And the second thing is that we can use a recent compiler proposed at Eurocrypt, which takes any 2-round OT with some specific security notions, which we prove our protocol has, and it can extend it into a two-round OT in the malicious setting, so where adversaries are allowed to arbitrarily deviate from the protocol, which is a much stronger guarantee than the one we obtained for the initial protocol. So this does eventually give us a two-round OT based on supersingular isogenies over FP squared with full malicious security in the UC model, which is great. Finally, we mentioned that we have also a three-round OT protocol, which is based on a different underlying mechanism. When we also prove security against semi-honest adversaries. And just to mention post-quantum, these two words have to figure in the presentation somewhere. All of this relies only on isogenies, so it's only built from post-quantum assumptions. So some further directions for this work is first to look at possibly other instantiations of the structure. Another work on OT from last year makes use of Kummer varieties, which could be another candidate. The next thing is to look at other potential protocol applications. So here we provide OT. Clearly, the key exchange also fits within our framework, but perhaps some other protocols or schemes can be created. And this would expand the possibilities. And finally, if an OT protocol could be built from the structure with native active security rather than relying on a transformation, this is also an open question. So thank you for listening. Hope to catch you at the live session. And if you have any questions, you can always contact me by email. Thanks.